Hello, welcome to a video on generation of a PWM signal using triple five timer. So let us first see what is this pulse width modulation. So we know that modulation is nothing but variation. So in very raw meaning, variation is modulation is a variation of something. Now here when it is said as pulse width modulation, so here it is a variation of the pulse width. So as the name itself indicates, so we are varying the width of the pulse. Now, in order to understand this variation of the pulse, so we need to understand a few terminologies. There is a modulating signal. So this is the one which is used to vary the pulse width. So we're going to have a modulating signal which is used to vary the pulse width, and we shall see without modulating signal, so there will be no variation in the pulse width. So if you don't have a modulating signal, the pulse width remains constant, so there will be no variation. So with modulating signal, so there is a variation in the pulse width. So this is what we are supposed to observe. So pulse width modulation is nothing but we are varying the width of the pulse with respect to the modulating signal. So here modulating signal is the one which varies the width of the pulse. Now we can see the pulse width modulating signal. It is pulse width modulation using a triple five timer monoshot. So using a monostable multiplier, let us see how do we generate a pulse width modulated signal. Now we know that it is possible to vary the pulse width by changing VTH of the triple five timer. We have studied in the previous videos. We know that VTH is the one which decides the pulse width of a monostable multivibrator. Suppose if you vary the value of VTH, then naturally you can change the pulse width. Now this is the key point. Now you apply this modulating signals at the control voltage. We know that VTH is the one which is connected to pin number 5 of triple five timer, which is also called as control voltage. Now instead of leaving the control voltage open or connecting it to capacitor, so let us connect the modulating signal to the control voltage. Now once you connect the modulating signal to the control voltage, we can observe the variation in the pulse width. So you can observe the variation in the pulse width of the modulated, the monoshot waveform. For that, so let us consider a monoshot pulse width of 0.11 millisecond. So that is without any external voltage, meaning with VTH as 2/3 of VCC. So we know that to have a 0.11 millisecond pulse width, so we are supposed to have a value of resistance, external resistance as 1 kilo ohm, and the capacitance required is 0.1 microfarad. So this is obtained using the equation T is equal to 1.1 R into C. Now in order to make the monoshot to work, we are supposed to have a trigger signal. Now we have studied in the previous videos that a trigger signal has to satisfy some criteria in terms of timing. Of course, one of the criteria is that trigger signal voltage should be less than 1/3 VCC, or it should be less than VTL in order to push the monoshot into positive stable state. That is in terms of voltage. In terms of the timing, the low voltage of the trigger should be less than the pulse width. Since we have taken the pulse width as 0.11 millisecond, let us have the time during which the trigger signal low, let it be 0.01 millisecond, maybe 10% of the pulse width. But we know that the time period of the trigger signal, the overall repetition time period should be more than the pulse width. Now here we are taking twice that of the pulse width. So here we have taken the pulse width as the trigger signal period as 0.22, which is twice of this. Now let us have around 20 cycles coming from the LT spice. So the number of cycles should be greater than 20. Now when we are now we are supposed to connect a modulating signal also to control voltage. Then what should be the type of modulating signal? What is a modulating signal? So modulating signal is one which is a sine wave. The time period of one cycle of the sine wave should be 4.4 millisecond. So we are considering this as 4.4 millisecond, so that we can at least have 20 pulses in one cycle of the sine wave, so that we can see the width variation. So in order to have at least 20 pulses within one cycle of the sine wave, the frequency is chosen as 220 Hertz. So let us see how does the LT spice simulation of this PWM look like. So let us try to see, okay, how does the waveform will look like. Now we shall okay, let us see the simulation of this mono shot for PWM generation. Here we have rigged up the mono shot for 555 using 555 timer. You can see we have a trigger signal of the signal going low for 0.01 millisecond, and it is repeating for every 0.22 millisecond. It has got more than 20 cycles, and the value of R is 1 millisecond, and the value of C is 0.1 millisecond. Here you can see we have left this CV open, meaning that the control voltage will be the default 2/3 of VCC. In this case, VCC is 5 volts, so the voltage at CV will be 3.33 volts. Now, if I simulate, I'll be getting the output voltage with its on time equal to 138 microsecond, whereas the pulse width will be of 0.11 millisecond. So that you can verify here. So we can have two cursors on either side of the on time. So you can see the pulse width is almost equal to 110 microsecond, that is 0.11 millisecond. So this is what is 109.9 microsecond, which is what is desired. Meaning, so since we didn't apply any modulating signal, the pulse width is constant. So let us apply the modulating signal and then try to find out how does this waveform will change. Let us apply a modulating signal. So for that, so let me apply the modulating signal in terms of sine wave. So I'm applying a signal now. Now let us go to this advanced. Let us have a sine wave. Let us have a DC shift of 2.5 volts, so that about exactly half of VCC will going to have the output varying from 2.5 till 5 volts, and it will go till 0 volts. So let us have the amplitude as 2.5. Sorry, DC shift is 2.5, and let us have the amplitude as 2.5. Let us have the frequency as around 200 hertz, and delay let it be 0. Let us have around 10 cycles. Yes, okay, let us see what happens now. Now the VC is 2.5, and over 2.5 we are applying a sine wave of amplitude 2.5 and a frequency of 200 hertz. Now let me see what happens to this. Now you can see there is a variation in the pulse width. So pulse width is keep varying. So you can see it is minimum the maximum width, and it is too much of maximum, the width reduces. If it is not clearly visible, so let me change this scale. So this scale is 5. Let me make it 5.5, and bottom let me make it around minus minus 0.2 volts, so that it will be more clear. Now you can see the width variation is happening. So let us see with respect to the modulating signal. So let me have the now you can see. So let me have the period slightly more than that. So let me just simulate up to around 5 millisecond and try to see how does. Now you can see the waveform is keep varying from 2.5, and it goes up to 5, and it is coming down. So let me slightly reduce the amplitude and try to have few more pulses. So let me not have the magnitude as 2.5. Let me just restrict it to 2, and see now how does the waveform looks like. Now we can see it is more clarity is there. Now the pulse width is keep on increasing, it is increasing, and you can see it is keep on reducing. So during the positive peak, you can see the width is maximum. When it is going to the negative peak, so when it is going towards negative peak of the modulating signal, the width is least. This way, so we can vary the width of the pulse by changing the modulating, by changing the voltage at the control voltage, that is VTH, by having a sine wave. So it is very important that the sine wave frequency should be small enough. So should be small enough. That means the time period of the sine wave should be large enough so that it can accommodate more number of cycles. Suppose if I include Suppose if I make the frequency a bit more smaller, and you can see now I won't have more number of cycles within. Let me just further increase the period here. This, let me make it around 10 milliseconds so that I can see one complete cycle. Now I can see the width variation is more clear. So there is more clarity in the width variation. Now this way we can do the PWM generation using the mono shot. Let us see if how do we is it possible to make the PWM generation using the Astable multivibrator. So it is also possible to vary the on time using by changing the value of VTH in Astable multivibrator. Now since it is possible to change the value of T on by changing VTH, now we can think of applying the modulating signal to control voltage so that T on changes. Now we have seen in the previous videos that T off of the Astable multivibrator with and without the external voltage will be constant. So once the variation of your T on changes with respect to VTH, then we want to have the width variation of the T on. Now this what is we are having a design with RA is equal to 1K and RB is equal to 1K, C is equal to 0.1, and without any external voltage the on time happens to be 138 and off time happens to be 69 microsecond, and you can apply a modulating signal so that again around 20 pulses of this on time off time come within one cycle, so the frequency can be 50 Hertz. And let us do one such simulation for an Astable multivibrator to generate a PWM waveform. Now this is a circuit diagram of Astable multivibrator using a 555 timer. So you can see to control voltage we have connected a sine wave. Now this Astable multivibrator now becomes a PWM generation. So we are applying a sine wave with a DC offset of 2.5 volts with a peak of 2 volts over this 2.5, and the frequency is 250 Hertz, and we have around 10 cycles. So let us now value of RA and RB of your usual resistance is 1K, 1K, and C is equal to 0.1 microfarad, which will give an on time of 138 and off time of 69 microsecond. Without this, let us see with this, okay, how does the width varies. Now we know that the voltage at the CV is changing as per the sine wave variation over that 2.5 volts, and we shall see how does the on time changes. Now you can see we are seeing 2 to 3 waveforms, 2 to 3 cycle of the input signal. The green one is the input signal, so let us put them in different planes and try to make out how do we differentiate the waveforms. So let me just put them in different planes. So this is input and this is the output what we have, the variation. To have a more clarity, let me change the scale here. So scale can be changed to a different value. So let me change this. To change the scale, let me click on this. Now the scale is top is 5. To have clarity, let me make it as 5.5 volts, and the bottom is 0. Let me make it as minus 1 volt. Now you can see the input is varying here. You can see now the input is varying. As the input increases towards 5, the on time is keep increasing. You can see everywhere the off time remains the same, meaning in case of VCO also we have seen in the previous videos, the off time of a 555 timer will not vary with the external voltage. Only you can see the on time is keep changing. The on time is increased, on time is slightly reduced. Now you can see reduced. Now we can see the on time is very small. Just have a look at this portion. Since the input voltage is going towards 0, the on time has reduced. Now again the on time is keep increasing because the voltage at VTH is keep on increasing, meaning the pulse, the on time of the Astable multivibrator is now decided by the modulating signal which is connected to the control voltage, which is actually changing the VTH value. So this way we can vary the on time of the sine wave, sorry, the square wave.